Here I am presenting my presentation which is based on automata and graph comparison. So before doing this, let's introduce the graph. What the graph is a very common set like data structure that consists of finite number of nodes and vertices. And here from the picture we can see that this is the node and this is the edge. The two nodes are connected with the help of edge. So when one represent a g of x y, it's a refer that the x is the vertices and this connected with the help of x is connected with the help of edge to the vertices y. So application of graph. So we are not going to put much effort on this topic, but we'll be go through that. So application of graph is data modeling. In wave graph, suppose we have in wave graph the URL. So we treat URL as a nodes and the link with the one URL to 2 URL with the help of edge. We can say that it is like a representation of graph from one URL to another URL. We have some link. So URL like a vertex and vertices, and the link is the edge like that. So this is the very basic of the we can with the help of graph it's define the flow of computation, and it is also used to represent the network of the communication and data organization. So why we are going to compress this, why we need to compress this? Because suppose we have a graph can be very bulky of size. So if you like when we want to traverse some information, essential data, so we have to traverse entire the things. So that's after the compression we are prone to traverse the less amount of path, and with the help of that we can easily traverse our data. And with the development of technology and all the things, the size of graph is become larger and larger. One survey says, the report says that in order of 100 of petabytes we have a size of graphs like that. So and we have also limited memory space, so we need to compress the graph so that we can handle this very easily and we can traverse our data very easy manner. So now with the help of finite automata we are going to do this in this paper. So let me introduce the finite automata. So finite automata is nothing but a finite state machine, and finite automata can be represented using 5 parameters: q, sigma, q naught, f and delta. And q is the set of all state, like here finite automata is here like similar to graph. So a, b, c, d are 5 set of states, and inputs where from we are going to start. So this is the arrow which is not starting from nowhere, so it is a source, like it is input. So in a graph we may have more than one inputs, and q naught is the initial state from where we are going to start, that will be treated as the initial state. In a graph we may have more than one initial state, but at the particular time we have one initial state, and f is a set of final states. So from suppose we are going to start from here, we can at that point can end with that point. We may have a different of ending point and the final states, but it will be denoted with the 2 circles. Here we have a starting point A, and C is our end point, final state, because we have denoted in the double circles. So this is our end point. So in our representation, this is the one source and one destination, final states. And delta is a transition function that map our path from where to where we are going. So it will be a tabular form from where with the help of weight. Suppose we are at a B, if input is a of j, then we will end with the C, and if we have a weight B of j, then we will end with the A. This is so delta will be determine the flow of transition from one state to another state. And automata is a very simplest model to compute the things and model of computation. So and this is a very limited memory. This is a very needy in our perspective, like for the graph. So we are using this finite automata concept to find some similarity in all the things with the graph, and we will apply this for the compression. So random automata compression. What is the random automata compression? The most of the real world data is very random in nature, and probabilistic model, whatever ergodic process models and all the things, probabilistic model for the automata generation is suitable for the mapping such type of data. And automata has some invariance property, so much property that is make it very useful to modeling of such type of data and all the things. And random automata is very similar to a stationary ergodic process of IDD sampling of data. So what is the now we are going to generate our graph in a very different manner and a very random manner, and we will correlate with, we can relate with this our graph to the automata, and we will apply something for the compression. So we use Erdos-Renyi model for the generation of the random type of graph. So it is used to implement a random graph generation. Suppose we have a g of xy graph that will be represent, we have a x nodes and m number of edges in our this model. If in we have a GNP, that model, it is also used to denote that graph is connected by the connecting nodes randomly, means p number of nodes out of n nodes, we are going to connect that nodes in very different and random manner. And the parameter p, here we have a model with, it is the p is the like a weight function, model increasing with the weight function. Suppose p is the p of the, suppose it is since it is a probabilistic model, so p is the increasing from 0 to 1. So here GNP, so on average we have a nc2 into p number of edges. For the one simplest model of graph, at least we need two nodes, means two node and one edge. So we have to connect. So nc2 means we are going to take nodes and edges to connect the things. So algorithm for the automata compression, we used Elias delta coding for the compression of our graph using automata model. So in Elias delta coding, what, let us understand the Elias delta coding with the help of example. Suppose we have a value x and we want to code that value x using Elias delta coding. So first step is to find L. So floor of L to x, so log x base 2. Suppose x is 12 for the understanding of x, so we will find L, it will be the floor of log x base 2 log 12, then we will find the values coming 3 and find L plus 1, it will be like a 4, and use the gamma Elias coding for the encode the L plus 1. Here what is the gamma Elias coding? We will find n is the L of log of L2 plus 1. Here L is 3, so L plus 1 is 4, so we will find n is equal to 2 and use unary code to represent the n. So we have 4 as a, and n is 2, so we will encode n with the 0. That is the 2 will represent 0 0 and 1, like we have to encode the unary with the help of unary code, and we will find L plus 1 minus 2 raised to power n using n binary bits. When we find this one, we will end with the 0, like L plus 1 is 4, 2 raised to power 2 is also 4, so it will be 0. So n number of binary bits, n is 2, so we will use to represent 0 with the help of 2 bits, and it will be 0 0. After that, gamma Elias encoding L plus 1, we will find the x minus 2 raised to power L, and we have the x is 12, L is 3, so 2 raised to power A is, it will be 8, and 12 minus 8 will be 4. So we will convert 4 in binary, and it will be give 1 0 0. To represent this positive integer x in Elias delta coding, we use this much of bits. Okay, so Elias delta code for the 12 is like 0 0 1 0 0 1 0 0. This will be length of 2 0 0 and 1. It will be unary code, then will be representation of 0 with the help of 2 bits, and then we'll append 4 in a binary version, so 1 0 0. And now, so in our algorithm, what we are going to do, we have inputs 0 to n, mean n is number of states. So x1 x2 is the number of states from where to where we are going to visit, from one source to destination. X1, suppose from we are going to traverse the nodes from 1 to 5 to 7 to 9 like that, and it will denoted x1 x2 x3 like that, and it will be up to the n, because we have at most n number of bits, n number of state, beg your pardon. So we use alias encode to encode the data x minus 1 x2 minus 1 like in recursive manner from one to another, and then next step from, suppose we have a 0 to 1, 2 to 5, 5 to 10, so we will encode the difference of that. Difference encoding algorithm we will demonstrate why we are using this for the such type of encoding. And from the literature and from the paper we find this one, we use at most this much of bits for encoding of this kind of sequence with the help of difference encoding algorithm. So why difference encoding algorithm for this? So mainly we have two type of graph to represent the graph. So adjacency matrix and adjacency list. So adjacency list we are not going to use because they require a lot of memory and lot of computation, and adjacency list is very tough to handle, but it's use very less number of memory, means very less memory. So that's why we are here to save our memory with the help of data compression. That's why we are going to use list. So if the state and node A is connected to the node D, and out of n number of nodes, so out of n nodes we are going to connect one node to the D number of nodes. So number of possible sets is NCD, and entropy of the state sets is log NCD. This will be almost D into log of n by D. So each state is need log n bits, then D into n time of bits we need for the encode entire D number of connections. So difference EA encoding, whatever we have previously I discussed, this will need this much of bits, and this will be D into log of n by D. This is very smaller as compared to this much. So that's why we are interested to use difference encoding algorithm. So Lampwell-Zilp algorithm with DEA, we are combining DEA algorithm in the Lampwell-Zilp algorithm. So what we are going to do, we will define first some parameter to further process. So D is our dictionary similar to the LZ, and DQ is expected number of transition from a node Q to another node, like E of Q is Q to Q1 with the weight A1, Q to Q2 with the weight A2, like a probability where A2, A1 like the weight of that node from where to where we are going with the what probability like that. So up to the Q to QD of Q. So T of D is the visited number of nodes, means which node we have visited, this will store in TD. TD is like a largest overlap of the transition. Which is largest number of transitions which we are going to visit the things. So it will be like a overlap, means which part we are going to cover the things. And T of sigma, alphabet of transition means which alphabet we have to cover, and we will store in T of sigma. And T of delta is transition from one state to another. So this parameter we are going to use. And in LZ algorithm, input is a transition level function delta of our automaton, like a transition we are going from where to where we are going with the help of which nodes, which path, like that. And finally we will encode our sequence S. So we will first set our dictionary as a phi, and we will visit Q using BSF model. In BSF model, breadth first search, it is a model to traversing a graph with the random fashion. So we are doing all the things in a supposing that we have a random data set in the real world. So that's why we are using BSF model for the every states and node. Q do what Q do, it will visit T of Q using log of mn bits, where m is size of alpha bits at the particular A nodes, and n is the number of states, present in that graph. And we will set T of D phi, T of sigma is phi, and T of delta is also phi. Initially we will set this, and we will start J at J1, and expectation of Q will start from Q to Q1, Q2 we have discussed this one earlier. So D up to this, and we will continue all to J up to the DQ, means we are used from initial to final up to the D of Q. We will trying to traverse all the nodes. Okay, so we are interested to find largest L such that a of I q of j to a of j plus 1 weight and paths from one initial node to largest number of we are wishing to traverse the things from 1 to j plus 1. Suppose from j is if 1, then j plus 1 is the length of this which L, like that. And we will this be, obviously dictionary will we have a largest size, so initially it is 5, but it can be up to the n since we are creating dictionary. And we will add this length d, we will say this one is a dr, and we will add to this in the dictionary. Okay, so this element we are supposing to that this is a dr, and we are adding this aj like that to our dictionary. All the element we are going to add in dictionary, and we will add d of r path of that in t of d maximum overlap whatever we have discussed, and d of this is final to the d of transition, and this weight to the alpha weight. Sum of that input we are going to add in t of d. All see, all are in integer form, because no difference, weight and all the things will be like whatever we are discussing node and the weight of that particular whatever data is presented, that we use to encode those things with the help of difference encoding algorithm. And this, since this is the weight, this is not integer, this is a weight, so we will use to encode this with the help of log m, so C of log m bits. So, and we will append this into the s. Since this will be also integer, this is also integer, that's why we use difference encoding algorithm to encode this one. And with the help this is not integer, this is a politic function, it may be a fraction of weight, so that's why we used to use store to this one to the log m bits to append this into sequences. And we will discard all the dictionary, and our output will be s. In this will be we append to this one. So if we don't use difference encoding algorithm, what will be happen? So we need cardinality of d into log of d of log d and log d number of n bits to encode the sequence, whether d is size of dictionary, n is total number of states, and m is size of alphabets. And if we use DE, difference encoding algorithm, then we need this much of bits, which is the very small as compared to this much. And the expression of this is written over there due to the time. Just not explaining the things. So experimental results. So we have experimental results. What we have experimental results? This is the class of the data G1, A1, G2, A2, and this is the sum for the same amount of data we are performing LZS. This is the advanced whatever we are using, and this is the compress. Compress. This is a unique compress command which is used in Unix system operating system. This is nothing but LZ78, and gzip is the Lemwell zip and G with the Walsh and Hoffman coding, and this is the LZA and plus GI. So for same amount of data we will perform this. And G1 is the directed Erdos Renyi graph, where we are randomly generated transition from the every source to destination with the probability of 1 by n, like kind of thing. So for the same amount of data, the compression, this is all are in after the compression in size of bits, size of bytes. So and A1 is the automata version of Erdos Renyi graphs, where there is a transition between the every two state here with the all source to destination, but here is one state to another, means every two state are traversing with the help of probability 1 by n kind of things. And then G2, where we are state we generate the data 1000 of bits like that in random fashion, and we connect every two state S and D with the probability of 1 by CS plus CD. This ensures the graph has a degree of varying from 2 to log of 2. I mean, the different kind of things. And A2, we generate transition with the above, and each transition will be a deterministic function of the destination nodes. In A2, we are going deterministic function, and A1, A2 is like a random. It will be G2 and A2 is like a deterministic. And if we compare this, we find this is the good with the some G1 and as compared to the zip and compress, but it is somehow LZ plus 1 zip is better than this. But the main advantage of the LZS over this one is the LZS over the existing algorithm ZS is just compress the structure, which is sufficient for the application in the speech processing and language modeling. And note that for the actual automata from the structure we need original state numbering, and with the help of that we can easily recover our data. That's why we use this one over the compression GZIP algorithm for our graph compression over this. And this is the references from where I have used to present that. Thank you.